for the popularity of fiber usage is materials with extraordinary strength can be obtained in their fiber form. Non-metallic fibers are usually showing a very high strength to density ratio compared to metal fibers because of the covalent nature of their bonds. The most famous example of this is carbon fibers that have many applications extending from sports gear to protective equipment to space industries. 81, 82. The stress on the composite can be expressed in terms of the volume fraction of the fiber and the matrix. Where is the stress? V is the volume fraction. The subscripts C, F and M are indicating composite, fiber and matrix, respectively. Although the stress-strain behavior of fiber composites can only be determined by testing, there is an expected trend. 3 stages of the stress-strain curve. First stage is the region of the stress-strain curve where both fiber and the matrix are elastically deformed. This linearly elastic region can be expressed in the following form. 81. Where is the stress, is the strain, E is the elastic modulus, and V is the volume fraction. The subscripts C, F, and M are indicating composite, fiber, and matrix respectively. After passing the elastic region for both fiber and the matrix, the second region of the stress-strain curve can be observed. In the second region, the fiber is still elastically deformed while the matrix is plastically deformed since the matrix is the weak phase. The instantaneous modulus can be determined using the slope of stress-strain curve in the second region. The relationship between stress and strain can be expressed as where is the stress, is the strain, E is the elastic modulus, and V is the volume fraction. The subscripts C, F, and M are indicating composite, fiber, and matrix respectively. To find the modulus in the second region, derivative of this equation can be used since the slope of the curve is equal to the modulus. In most cases it can be assumed since the second term is much less than the first one. 81. In reality, the derivative of stress with respect to strain is not always returning the modulus because of the binding interaction between the fiber and matrix. The strength of the interaction between these two phases can result in changes in the mechanical properties of the composite. The compatibility of the fiber and matrix is a measure of internal stress. 81. The covalently bonded high-strength fibers, for example carbon fibers, experience mostly elastic deformation before the fracture since the plastic deformation can happen due to dislocation motion. Whereas, metallic fibers have more space to plastically deform, so their composites exhibit a third stage where both fiber and the matrix are plastically deforming. Metallic fibers have many applications to work at cryogenic temperatures. That is one of the advantages of composites with metal fibers over non-metallic. The stress in this region of the stress-strain curve can be expressed as where is the stress, is the strain, E is the elastic modulus, and V is the volume fraction. The subscripts C, F, and M are indicating composite, fiber, and matrix respectively, and are for fiber and matrix flow stresses respectively. Just after the third region the composite exhibit necking. The necking strain of composite is happened to be between the necking strain of the fiber and the matrix, just like other mechanical properties of the composites. The necking strain of weak phase is delayed by the strong phase. The amount of the delay depends upon the volume fraction of the strong phase. 81. Thus, the tensile strength of the composite can be expressed in terms of the volume fraction. 81. Where Ts is the tensile strength, is the stress, is the strain, E is the elastic modulus, and V is the volume fraction. The subscripts C, F, and M are indicating composite, fiber, and matrix, respectively. The composite tensile strength can be expressed as 4 is less than or equal to arbitrary critical value of volume fraction, 4 is greater than or equal to the critical value of volume fraction can be expressed as evidently. The composite tensile strength can be higher than the matrix if is greater than. Thus, the minimum volume fraction of the fiber can be expressed as although this minimum value is very low in practice, it is very important to know since the reason for the incorporation of continuous fibers is to improve the mechanical properties of the materials /composites, and this value of volume fraction is the threshold of this improvement. 81. The effect of fiber orientation. Aligned fibers. A change in the angle between the applied stress and fiber orientation will affect the mechanical properties of fiber-reinforced composites, especially the tensile strength. This angle can be used to predict the dominant tensile fracture mechanism. At small angles, the dominant fracture mechanism is the same as with load fiber alignment, tensile fracture. The resolved force acting upon the length of fibers is reduced by a factor of from rotation. The resolved area on which the fiber experiences the force is increased by a factor of from rotation. Taking the effective tensile strength to be and the aligned tensile strength. 81. At moderate angles, the material experiences shear failure. The effective force direction is reduced with respect to the aligned direction. The resolved area on which the force acts is. The resulting tensile strength depends on the shear strength of the matrix. 81. At extreme angles, the dominant mode of failure is tensile fracture in the matrix in the perpendicular direction. As in the isostress case of layered composite materials, the strength in this direction is lower than in the aligned direction. The effective areas and forces act perpendicular to the aligned direction, so they both scale by. The resolved tensile strength is proportional to the transverse strength. 81. The critical angles from which the dominant fracture mechanism changes can be calculated as where is the critical angle between longitudinal fracture and shear failure, and is the critical angle between shear failure and transverse fracture. 81. By ignoring length effects. This model is most accurate for continuous fibers and does not effectively capture the strength orientation relationship for short fiber reinforced composites. Furthermore, most realistic systems do not experience the local maxima predicted at the critical angles. 83, 84, 85, 86. The Tsai-Hill criterion provides a more complete description of fiber composite tensile strength as a function of orientation angle by coupling the contributing yield stresses, and. 87, 81. Randomly oriented fibers. Anisotropy in the tensile strength of fiber-reinforced composites can be removed by randomly orienting the fiber directions within the material. It sacrifices the ultimate strength in the aligned direction for an overall, isotropically strengthened material. Where K is an empirically determined reinforcement factor, similar to the particle reinforcement equation. For fibers with randomly distributed orientations in a plane, and for a random distribution in 3D. 81. Types of fibers and their mechanical properties. The most common types of fibers used in industry are glass fibers, carbon fibers, and Kevlar due to their ease of production and availability. Their mechanical properties are very important to know. Therefore the table of their mechanical properties is given below to compare them with S97 steel. 88, 89, 90, 91. The angle of fiber orientation is very important because of the anisotropy of fiber composites. Please see the section Physical Properties for a more detailed explanation. The mechanical properties of the composites can be tested using standard mechanical testing methods by positioning the samples at various angles. The standard angles are 0 degrees, 45 degrees, and 90 degrees, with respect to the orientation of fibers within the composites. In general, 0 degrees axial alignment makes composites resistant to longitudinal bending and axial tension /compression. 90 degrees hoop alignment is used to obtain resistance to internal /external pressure, and plus or minus 45 degrees is the ideal choice to obtain resistance against pure torsion. 92. Mechanical properties of fiber composite materials. Fibers at 0 degrees, UD, 0 /90 degree, fabric. To loading axis, dry, room temperature, VF equals 60%, UD, 50%, FA symbol units standard carbon fiber fabric high modulus carbon fiber glass fabric Kevlar fabric standard unidirectional carbon fiber fabric young S modulus 0 degree E1 G par 708525301335 young S modulus 90 degree E2 G par 7085253010 in plane S shear modulus 12 G par 55455 major Poisson S ratio 120.100.100.200.200.30 alt. Tensile strength 0 degree par 600350440480150 alt. Comp. Strength 0 degree par 5701504251901200 alt. Tensile strength 90 degree. Par 6003504404805 alt. Comp. Strength 90 degree par 5701504251901250 alt. In plane shear string. SM par 9035405070 alt. Tensile strain 0 degree extension percent 0.850.401.751.601.05 alt. Comp. Strain 0 degree excellent percent 0.800.15.700.600.85 alt. Tensile strain 90 degree it percent 0.850.401.751.600.50 alt. Comp. Strain 90 degree percent 0.800.151.700.602.50 alt. In plane shear strains percent 1.800.701.001.001.40 density /cc1.601.601.901.401.60 Fibers at plus or minus 45 degree to loading axis, dry, room temperature, VF equals 60%, UD, 50%, fabric, 93, symbol units standard carbon fiber high modulus carbon fiber rear glass standard carbon fibers fabric glass longitudinal module use 1 GPA 171712.319.112.2 transverse module use 2 GPA 171712.319.112.2 in plane shear modulus 12 G par 33471130 Poisson S ratio 12.77.83.53.74.53 tensile strength par 11011090120 compressive strength par 11011090120 in plane shear strength par 26021010031015 thermal expansion coef alpha 1 strain forward / K2.15 E60.9 E612 E64.9 E610 E6 moisture coef beta 1 strain forward / K3.22 E42.49 E46.9 E4 Mechanical properties of aerospace grade and commercial grade carbon fiber composites, fiberglass composite, and aluminum alloy and steel. This table is demonstrating one of the most important features and advantage of fiber composites over metal. That is specific strength and specific stiffness. Although the steel and the aluminum alloy have comparable strength and stiffness with fiber composites, The specific strength and stiffness of composites are around higher than steel and the aluminum alloy. Comparison of cost, specific strength, and specific stiffness. 94. Carbon fiber composite, aerospace grade, carbon fiber. Composite, commercial grade, fiberglass composite aluminum 6061 T6 steel mild cost $/pound $20 $250 plus $5 $20 $1.50 $3.00 $3.0.30 strength. Psi 90,000 200,000 00050 000 90,000 20,000 35,000 00060 000 stiffness. Psi 10x 10650 x 1068 x 106 10x 1061 x 106 1.5 x 10,610 x 10,630 x 106 density. Pound / in 3 0.0500.0550.0550.100.30 specific strength 1.8 x 106 4 x 1061 x 106 1.8 x 363,646 36,350,000,000,000 specific stiffness 200 x 106 1000 x 106,000 160 x 106 to 200 x 10,618 x 106 to 27 x 106,000 100 x 106,000 100 x 106. Failure. Shock, impact, or repeated cyclic stresses can provoke the laminate to separate at the interface between two layers, a condition known as delamination. Individual fibers can separate from the matrix. For example, fiber pull-out. Composites can fail on the macroscopic or microscopic scale. Compression failures can happen at both the macro scale or at each individual reinforcing fiber in compression buckling. Tension failures can be net section failures of the part or degradation of the composite at a microscopic scale where one or more of the layers in the composite fail in tension of the matrix or failure of the bond between the matrix and fibers. Some composites are brittle and possess little reserve strength beyond the initial onset of failure, while others may have large deformations and have reserve energy absorbing capacity past the onset of damage. The distinctions in fibers and matrices that are available and the mixtures that can be made with blends leave a very broad range of properties that can be designed into a composite structure. The most famous failure of a brittle ceramic matrix composite occurred when the carbon-carbon composite tile on the leading edge of the wing of the Space Shuttle Columbia fractured when impacted during takeoff. It directed to the catastrophic breakup of the vehicle when it re-entered the Earth's atmosphere on the 1st of February 2003. Composites have relatively poor bearing strength compared to metals. Testing. Composites are tested before and after construction to assist in predicting and preventing failures. Pre-construction testing may adopt finite element analysis, FEA, for ply-by-ply analysis of curved surfaces and predicting wrinkling, crimping and dimpling of composites. 95, 96, 97, 98. Materials may be tested during manufacturing and after construction by various non-destructive methods including ultrasonic, thermography, xerography and X-ray radiography, 99, and laser. Bond inspection for NDT of relative bond strength integrity in a localized area. See also. Aluminium composite panel. American Composites Manufacturers Association. Chemical vapor infiltration.
Yes,
Composite
let's stop the
Epoxy
video.
granite.
Stop the video.